Good evening and welcome to Exploring Black Holes. Today we're delighted to have Dr. Jeffrey McClintock of the Harvard-Smithsonian Center for Astrophysics to speak to us on X-ray binaries and the search for black holes. Dr. McClintock was an MIT graduate student and got his PhD a little while ago, but since that time has made a terrific name in the observational search for black holes. And in fact, he did some of the pioneering work that he's going to report on today. Is the mic okay? Okay. Just want to make sure that we're audible here to the audience. So we're delighted that Jeff could come down from the CFA, and he'll be using the transparencies this evening and telling us about the search for black holes in X-ray binaries. Welcome, Jeff.
Thanks. In this short time, I can only give you a rough idea of the kinds of things that we do. And if you want to get the whole story, I suggest that you get this book, Compact Stellar X-ray Sources, which won't be out till 2004, but the articles will be listed in Astro PH this year sometime as they get done. Mine is not yet done. But these are 3 of the 12 articles in the volume, and they all deal with the kind of material that I'll be talking about today, but in great detail with all the references and all the information. So I can only hint at the kinds of things we're doing in the short time that I have today. We're talking here about stellar mass black holes, which have been formed from the collapse of massive stars. And there are believed to be about 10 to the 8th to 10 to the 9th of these in the galaxy out of 10 to the 11th stars. So you can see that there's a very large number of these objects. And we only know about a very small number, which I'll come to here in a moment. We believe that about 1,000 of these are in mass exchange binaries, meaning that the black hole is close enough to an ordinary star that the ordinary star can deposit matter over onto the black hole. And when that happens, we see X-rays. We see very energetic light from the material falling into the deep gravitational potential well of the black hole. And of these 1,000 that are believed to be in these close mass exchange binaries, most of them are dormant, so we haven't seen them go off yet. And the time between when they go off is maybe 100 years, 200 years. No one knows quite what the duty cycle is, and they're only on for a year or so. They're transient systems. And the number that we've measured the masses in, which is really the most important subset of these objects, are 18 objects. And I'll come back to this a little later. Now, these black holes have a lot of significance to astronomy. They're obviously an endpoint of stellar evolution. They're very important to people who compute supernova explosions because it's very hard to do that, and you'd like to know what the mass of the remnants are, the black holes that are formed. So we measure the masses of these. That gives a constraint on those kinds of models. And the stars that form these black holes also spew a lot of enriched material into the interstellar medium. So it's very important to what's called cosmochemistry as well. I could go into all of those things too, but I'm going to skip all of that because I know this is a course in general relativity. So I'll cut right to this significance of black holes to physics, because the significance of these black holes to physics is that we may be able to make a test of general relativity in the strong field gravitational limit. And that's the importance of these black holes, at least for this evening's discussion. Now, there's 2 kinds of black holes. Well, there's more than 2, of course. There's a gradation between them, but the Schwarzschild black hole is an idealization. It's a black hole that isn't rotating at all, and I'm sure you've had this in your course. And this parameter A star indicates how much rotation there is, and it goes from 0 to 1. For an extreme Kerr black hole, it's 1, but any black hole might be anywhere in between 0 and 1 in terms of this parameter. It's just a dimensionless measure of the angular momentum of the black hole. And if you take a Schwarzschild black hole, well, I've just said, let's make it 10 solar masses. You'll see that's a very typical mass for the masses that we measure for these black holes. Then the radius of that black hole is just 30 kilometers, and it scales directly with a mass. So it just gives you a feeling for the size. There is a last stable orbit as you get into the strong gravitational field. I don't know that you've covered this in the course, but it's out at 3 Schwarzschild radii. And inside there are no stable orbits. The material tumbles in quickly. So that's really where we see an accretion disk of material, which I'll come to in a moment, as it being terminated on the inside at 3 Schwarzschild radii. For an extreme Kerr black hole, the numbers are shown here. Again, I say 10 solar masses just for illustration. And the radius of the event horizon in this case is 15 kilometers, half of what it is here. And obviously then you can, then even more important, the last stable orbit, prograde orbit for the black hole, material orbiting in the same sense as the hole is rotating, is also 15 kilometers. So this is a very, the point is you can get a disk going right on down into the very deep gravitational potential well, much more so than you can in the case of the Schwarzschild black hole. So you can expect, much greater energy releases here. And the energy release here can be 6% of mc squared. When you drop material in, you can get 6% of the energy out. Here you can get up to 42%, theoretically. A very important number for the kind of thing we'll come back to in a moment is that the maximum frequency in this last stable orbit here is 220 hertz for a 10 solar mass black hole. And this scales inversely as the mass. So the more massive the black hole, the larger it is, the slower will be the orbit. So this is for a 10 solar mass black hole. And for an extreme Kerr hole, you see you can get to much higher frequency. So that's something we can measure. We can hope to measure, and I'll show you that we have some evidence of measuring it, which is very important. Now, I just want to remind you, so this won't be completely abstract, that these black holes just come from O stars. And this is, they come from massive stars, like 40 solar masses, 30, 40, 50 solar masses. And such stars only last a couple million years. This is a cluster of them here, a few hundred O stars in 30 Doradus, which is in the Large Magellanic Cloud. And those stars don't last any longer than humans have been on the Earth. I mean, a couple million years, which is really nothing in astronomy. And of course, when they've burnt their fuel out, they collapse. And they may shed a lot of material as wind before they collapse. And they may also produce a violent explosion that blows a lot of material out into the interstellar medium. But this core goes on down, and nothing can stop it. And you get complete gravitational collapse of matter into a singularity. And it's cloaked, of course, in this event horizon. So that's where they come from. That's where the 100 million to a billion come from. And there aren't very many O stars in the galaxy just because they don't live very long, right? And so they're always being cycled, born, and then dying into black holes. Now, there's some abstraction to all of this, so I brought one slide that cuts maybe through some abstraction. At least it's one way of saying, what does it mean, to go to complete gravitational collapse of matter? I mean, I don't think anyone really has a good feeling for that. I mean, everything in this room, everything, the oceans, the whole crust of the Earth, the whole solar system, the whole sun, everything going to a point. We don't have too much feeling for that, I don't think. I mean, it's rather abstract. So I have this one illustration that I put in a popular level article one time, which shows pressure on this axis for various objects. And it starts at sea level, and this is atmospheres here. So 1 atmosphere is sea level right here. And then when you're down 200 miles into the Earth, you get pressure of about where diamonds form, you get about 1 million atmospheres and so forth. In the center of the sun, you get about 10 to the 10th atmospheres. Center of a white dwarf. Center of a neutron star, you get 10 to the 28th atmospheres. Well, I don't know how many of you work with atmospheres, but a few atmospheres is all it takes to scare you. If you have something, a pressure vessel or something, and it's at a few atmospheres and a window might break, and it can be kind of violent. Or if you've ever pumped water up 5,000 feet up a hill or something, and you just have to deal with the seals and the pumps and so forth, you get a feeling. Or if you've ever seen material that's been crushed in a deep submersible in the ocean or something at 30,000 feet, you get some idea for pressure. At 10 to the 28th atmospheres, it's an incredible pressure, but that's the pressure that's pushing on the center of a neutron star. And the problem, of course, is that that pressure is so great that it's at the point where it's ready to destroy the matter. And a neutron star is very close to going under and into a black hole. And in fact, there is some limiting mass of a neutron star, not well known, not really known, but around 3 solar masses, perhaps 2 solar masses, where if you just put a little bit more on it, it will go because the gravity is so powerful. And at this point, the pressure force is actually 1/10 of rho c squared. So it's a tenth of the matter energy density of the material. So it's already very significant. Source of gravitation, which is so ironic because it's the thing you count on for holding the star out, the pressure force. But now it's gravitating at about a tenth of what the mass is in the star itself, just because that's its energy that's holding off this collapse. And so all of a sudden the pressure is turning traitorous by making this, because it's got energy, it's got mass, and it's causing. So you say, okay, well, let's just crank up the pressure a little more. But if you crank up the pressure to stop the collapse, of course, you're just producing more gravitating matter by E equals mc squared, the energy in the pressure field. So it's, and you see this if you look in the Oppenheimer-Volkoff equation. Maybe you've had that, the equation for hydrostatic equilibrium in general relativity. So it's really very difficult. And obviously, I don't put the black hole on here because we don't speak of the pressure. It's unspeakable. It's off the graph totally. Now, I'll start talking about the black hole binaries, which are the objects that I work on. And this is a schematic drawing, sort of an anatomy of one of these. And this is a sort of a typical one. I'll show you a schematic that shows 14 of these objects, but this is just one of them. And what you have here is a star that's tidally distorted, an ordinary star like the sun, tidally distorted by the gravity of the black hole, which is here in the center of this disk, which is an accretion disk. So what one imagines is material flows through from this inner Lagrangian point here and flows on to this accretion disk and goes into orbits and finally winds its way down into the center of the black hole. So this is for a system with a period of about 1 day, and again, about a 10 solar mass black hole. And interestingly, the black hole down in the center here, I've expanded it and shown it here, is only about 30 kilometers across. And the ratio of this size, the black hole size, to the size of this orbit here is about the ratio of an atom to its nucleus. You know, it's the same 10 to the 5th, more or less, that you're familiar with. Not that that has any connection to this, but I mean, it's just the scale is very large, is what I'm saying. That little object in the center with 10 solar masses. And of course, the object is actually much smaller than this event horizon. It's something down inside here we don't know very much about. But this is the kind of object we're dealing with. Now, we've measured the masses of 18, actually, and these are 14 of these systems here that I've drawn in on a picture here. Actually, my colleague Jerry Arose drew them, and you can see that they range from tiny little systems like this one here. These are just the same kind of sketches, a sketch I just showed you with a star and a black hole and this disk of material around the black hole. And this one here, for example, has a 4-hour orbital period. This one up here, and they're all drawn to relative scale here. You know, all drawn to schematic relative scale. So this has a 35-day period. This is the giant, and this is 4-hour period. So this is a tiny little system. And then you can see they vary in different periods here. The orbital period pretty much sets the size of the system. And you can see we've actually measured the inclination of the orbit too. So you can see, for example, this system is almost face on, as this sketch would indicate. You're looking right down on the plane of the disk almost in that system. Whereas some of them are more edge on, as you can see here, for example, nearly edge on. We don't yet have an eclipsing system, which of course we'd love to have, because then you might be able to see the stars swing in front of the X-ray emitting region around the black hole and map out the X-ray emitting region around the black hole with this disk of the star going in front of it. So we're extremely excited about the possibility of finding such an object, and I don't want to go into that anymore because we have some plans in that direction. Now, this is a painting of these kinds of things, and there's two states of these systems, and I'll come to that in a moment. They get either extremely luminous when they go off for a year or so, and then they get extremely faint, and when they're faint, they remain faint for perhaps 100 years. I mean, this one in particular is sketched for a particular system I worked on with Ron Remillard here at MIT. It's called A0620-00. They're all by their coordinate names, so they're not very pretty names. And this is a little K5 star, a little smaller than the sun. And you can see the material dribbling over into this accretion disk, and the black hole is down here in the center. And this is just to give you an idea what it might kind of look like in its quiescent state. But when it becomes extremely luminous, what happens is not that a lot of material comes over from this star onto here, but that all the material stored in this disk suddenly breaks loose like a dam. The disk goes unstable, it suddenly gets hot, and the material gets viscous, and the material can then fall down onto the, quickly wind on down to the black hole at a very high mass accretion rate onto the black hole. But it isn't because this star suddenly erupts. It's because this disk, which has been dammed up for 100 years, suddenly goes into an unstable state. And I don't have a picture of what they might look like in a violent outburst, but you get the idea. Now, for the same system that was drawn for, A0620, I show here what happened in 1975, which was measured by the MIT SAS-3 satellite and other satellites too. And the system got up to 10 to the 38 ergs per second. And that's, I don't know, 10,000 solar luminosities or so, but all in pure X-rays. Okay. And then it decayed over a period of about several hundred days, which is about a year, like I said. And it goes from 10 to the 38 ergs per second down to the 10 to the 30th. So this is the quiet phase that last painting was for. And this is the outburst phase up here. And we discover all of these objects in outburst. We don't discover them in the quiescent. We have never discovered one in the quiescent phase. We discover them when they're brilliant and easy to find, and then we follow up on them later when they quiet down. And when they quiet down, we can measure these masses that I will talk to you about. The optical object also gets bright. It gets bright only by a factor of about 1,000 or so. So the optical object gets bright, and that brightness is mostly the X-rays slamming into that accretion disk, heating the accretion disk, and producing a very brilliant, 35,000 degree source. And that's what you see as the accretion disk. And then when you come down like this and you get back into the quiescent phase here, you see about half the light from the accretion disk and about half the light from the ordinary star. And this is the very nice thing about these systems. They get so quiet. See, 10 to the 30th ergs per second in X-rays is so little that it doesn't affect the star very much. So you get a very clean star to measure, and you can measure the radial velocities of that star very accurately. And then you can measure the mass of the black hole. And that's one of the major things that we've done with these objects. Now, this is a very elementary idea, but I just want to make it maybe less abstract. Of course, Newton did gravity in 1687. You still couldn't measure masses until Cavendish in the laboratory measured G. And together, you can put the formula in this form or some other forms if you would like. And in this form, you can then go ahead and measure the mass of the sun, for example, by looking at the orbit of the Earth around the sun, by sticking in the velocity of the Earth, the orbital period, where it's 1 year, right, and 2 pi g, and you can then get the mass of the sun. Or you can get the mass of the Earth in the same way. Or you can get the mass of Jupiter from Eo's moon. And so you get solar mass, 3 microsolar masses, a millisolar mass. And we've known this now for a long time. And so this is one thing we really, it doesn't matter that you're studying black holes. This is simple dynamics. So this works, and you don't have any doubt about it. And that's what's so good about it. Of course, there are little complications, and they'll come in a moment, because we don't know the mass of the, if this were a point particle, like a little light satellite going around the Earth, that would be one thing. But the moon, of course, has some mass, so you have to take that into account. You have to really determine the mass of the moon independently if you really want the mass of the Earth accurately by measuring it in this fashion. So it's just a detail. Now, for these objects, this is some of the best data that we have for these objects. This is what's called a radial velocity curve for one particular system, V404 SIG, with a period of 6.5 days. And all you do is you look at this star with a telescope, and you're measuring the spectrum of the optical star. And you see that, of course, for a while it's moving away from you, and the light is redshifted, and then it's moving transverse to your line of sight, and it's not shifted, and then it's coming toward you. It's blue shifted. And so basically that's what this curve is here. And you do this by, we have cross-correlate the cross-correlate the optical spectrum of the star that's orbiting the black hole against the spectrum of a field star, which is stationary or moving at a constant velocity. And then we get this curve. That's all it is. It's very simple. And the two numbers you get from this curve immediately are the orbital period, because that's just the time from max to max, and you get this semi-amplitude of the velocity curve. And those two numbers are all you need to get the absolute minimum mass of the compact star that you're dealing with. What you're measuring then is you measure what's called the mass function. This is the mass function. And by measuring the period and the semi-amplitude, and you have constants here, you can calculate a number, and in the right units, you can have it in solar masses. For this system, it comes out to be 6.1 solar masses with this uncertainty. Over on this side of the equation, you have this M1 is the mass of the black hole. M2 is the mass of the optical star. So it comes in here. And if you really want to get M1, the mass of the black hole, which we do, then you have to get M2, the mass of the other star. But more important than that, you need all you're measuring is the velocity in the line of sight. And this orbit could be tilted to you like this or like this. So you need that tilt. You need that angle of inclination of the orbit. That's the I that's in this equation. So to get the mass, you really need both of them. But without getting those, just by measuring this, you can say that the minimum mass of that compact star in this system, it can't be less than this value right here, the value of the mass function. It can't be less than 6 solar masses. And I could show that, but it isn't too important to do it, I don't think. The main thing here is how massive can a neutron star be? And there you go to general relativity. And general relativity says, and there's proofs of this, that 3 solar masses is as massive as you can go in general relativity, unless you make some extraordinary. There's some slight conditions on that. For example, if you want to set a limit of 3 solar masses on the mass of a neutron star, then you have to say that you know the equation of state up to some density in the crust or in the outer part of the star, and you also have to make the assumption that dp d rho, which is the velocity of usually the velocity of light, the velocity of sound rather in material, dp d rho is you have to assume that that's less than c squared, and most people accept knowing the equation of state up to some fiducial density, like maybe 1-2 times nuclear density or saturated nuclear density, like an uranium nucleus, and they assume that dp d rho is less than c squared, and so most people say 3 solar masses is a really hard limit on the mass of a neutron star. But even if you drop those assumptions, it only goes up to like 6 solar masses or so. So you do need general relativity to make the claim that these things are black holes, and so that's what the data looks like for the mass. Now, you can measure the mass function of all of those that I had in that earlier picture. And when you do that, you get the mass function being a lower limit on the mass of the black hole. You get some of them. In particular, this is the one we just looked at 6 solar masses right here. You're saying that the mass of the compact object is greater than 6 solar masses, and this one likewise, and so forth. This group here, they're diamond hard black holes. I mean, they're not even in question. I mean, there's no way that it couldn't be black holes, and this is not yet taking into account that these are minimum possibilities. The masses will only be greater than this once you determine the inclination and once you determine the mass of the secondary. So this group here are certain black holes, and these are extremely good black holes as well. These require extra supporting information, like you really do need the inclination of the orbit to make the case that these are black holes. So then you go on and you measure the mass of the black holes, and those measurements are not so easy because the measurement of the radial velocities is very straightforward. There's no systematics. It's extremely simple. But to measure the inclination and to measure the mass of the secondary is a bit more of an art, which means it's a little less certain. Nevertheless, you can do it, and there are techniques which I won't describe now. But when you do it, you get the masses of the black holes as shown here. These black dots are the minimum are the minimum limits that I mentioned before. And these open circles with the error bars are the actual masses inferred by measuring the inclination and the mass of the secondary star. And you'll see that the masses are generally right around 9 or 10 solar masses. And you'll also see that there are a few that are well measured. I think we have the capacity now, of course it depends how well behaved a given system is, to improve a lot of them to this level, which would be, of course, a major advance because you can use these masses for quite a few things. I already mentioned one thing, namely the supernova explosions, and you try to determine the masses of the remnants that are left. You can put better constraints and you get a better mass distribution than this. So this is what's been done in terms of measuring the masses of these objects. Now, of course, you want to do something better than just measure mass, because measuring mass is still not yet satisfying in terms of general relativity, in terms of strong field gravity. You want to measure something now very close in to the black hole. That's what you really would like to do. Some physics there that you understand, and there are a few possibilities, and I'll mention just a couple of them. One of them that people talk about is measuring, and there have been some measurements of lines like this. The accretion disk, the very inner accretion disk, which is truncated at the last stable orbit, as we said, has very strong gravity, or can have very strong gravity, and that strong gravity can have an effect on a spectral line that's being emitted by the disk. And this is a schematic indication of how that would go. There's emitters that are here. For example, iron is the line to look at, because it's the iron line is the one that remains at at the energies and temperatures of the inner disk and everything. So, and iron is also a very abundant species, and so it's the one that one works on. And the iron line, you see iron emitters in this disk, and they're coming toward you. So that will blue shift. The emission that's coming from that region will be blue shifted, and this region will be red shifted. There's gravitational redshift that you have to take into account. That's indicated here. This is a schematic idea of what an iron line would look like. If the iron atoms were all at rest, it would just be a sharp line right up. Well, it'd be more like up here. And then all of these effects, namely the Doppler, the longitudinal Doppler effect in the disk, which affects obviously the place at which a particular emission is registered by you, and also the gravitational redshift, just by the strong gravity pulling, and that moves everything toward the red part of the spectrum. And then there's also the transverse Doppler shift, just in this, it's like second order Doppler shift, which we don't usually talk about, but is certainly important here. So those three things, the longitudinal, transverse, and gravitational redshift, shape this line into a shape like this. These are simulations by a theorist by his name of Chris Reynolds, and I really liked his energy scale, 3, 5, 6, 9. I mean, it's I would never do that, but but in any case, I could have brought a real profile, but there are profiles not as good as this. This is what we hope to see from the new ConX observatory that's being studied right now and to be built soon, hopefully. And this shows that you can tell a difference between a Schwarzschild black hole and a Kerr black hole. The Kerr black hole, you have the stronger gravitational redshift out here because you get down deeper into the gravitational potential well. And the Schwarzschild black hole gives you a bigger spike there. And so you can tell the metric. You can get the rotation of the black hole from this. And in principle, the thing about this is you are making an assumption, because you have to know, I just said that the iron atoms are emitting from this disk, but why are these iron atoms emitting from this cold disk? The reason they're emitting from this disk, which really isn't that hot, is because there is a corona of hotter X-rays, which I haven't talked about, that are shining down onto the disk and fluorescing the X-rays up out of the disk. That's the model. So if you're going to make such a model and try to solve for things, you have to have an idea of what that hard radiation is, that radiation from the corona that's fluorescing. You have to have a model for that. And that seems to be changeable. That seems to be, but it's the kind of thing that if you had enough data, you really feel you could put it together. You could make some sense out of it. You could get a consistent model of what that X-ray emitting, hot X-ray emitting gas is above and below the disk, and also determine the metric. Now so that's spectroscopy, okay? Now another technique that's extremely important is timing data. And this is from the X-ray Timing Explorer. And at MIT here, they've had a lot of participation in the Rossi X-ray Timing Explorer, which was launched in January 1996. And this satellite, its purpose was it's still there, is to measure the time of the X-rays as they come in. And for sources that aren't too bright, it can actually measure every X-ray to a microsecond, the time that it came in. And you'd say, well, so what? Well, I mean, maybe it's just kind of a vanilla and nothing's happening and all that. But here, I'll just show you one source. This happens to be a pretty good source. And on the top is a power spectrum. And this is like a Fourier transform squared, more or less. And when you take such a Fourier transform of this system, this is for a 3,000-second observation of this particular black hole X-ray nova. What you see is a big thumping frequency here. But it's not monochromatic, you see. It's not like a pulsar or something. It's in one frequency bin. It's in a wide range of frequency bins. So it's a quasi-periodic oscillation. It isn't constant in phase, it appears. It seems to wander in phase. Nevertheless, it gives you quite a big spike. And you can see here also some satellite harmonics that appear here, too. And we had something like 340 observations of this source with the RXT that are like this. And something like 200 of them showed power like this. So it isn't just that you get it once. You get it a lot of times. And you see a lot of regularities. And I'll come to that in a moment. But just to give you a feeling, it doesn't look like much because it's a log scale. You have to keep an eye on the log scale here. So if you just plot it as a time series, this is 0 counts here per 16 milliseconds. And it goes up to like 100 counts per 16 milliseconds. This is a 10-second record. So here you see the time series that makes this QPO pattern. So it's huge. Now, the source is radiating at like 10 to the 39 ergs per second in X-rays. And something like 25% of the photons that are being emitted, a quarter of that 10 to the 39 ergs per second, are thumping away like this. So this isn't an incidental detail on the accretion flow or on the phenomena. It's really extremely important. And the frequency of this is, these are what we call low-frequency QPOs, meaning they're below 30 hertz or so. And this one happened to be 2.7 hertz, but it varies at different days. It moves smoothly. It correlates with the spectral parameters. There's a lot of information you can get from this. But we're not as interested in this as we are in the one I'm going to show you now. Because this is a low frequency, and it probably comes from pretty far out. It doesn't have to come, from close in. It doesn't have the dynamical time of that 200 hertz or that 1500 hertz I was talking about at the beginning, which is a time of the disk to go around. No, it's much further out. And neutron stars can produce this to some extent, too. So this is something that no one understands, really, in terms of model or anything. And we would all love to understand it, what is driving this and how it works and so forth. But I will turn now to a more important aspect of these quasi-periodic oscillations. And this is the high-frequency QPOs. And this is for another system, 1655 minus 40. And what you see, again, is a power spectrum. And we can't even make the time series here because this is 450 hertz. What does it say? Yeah, it's here. It's 450 hertz, right? 450 hertz. You can see it here on the axis, too. Okay, so this is quite serious now, 450 hertz. This is a very high frequency. So where would this be coming from? And we believe that the clock that's producing this is really the disk rotation. And already you learn something from 450 hertz. And what you learn from 450 hertz is that if you take the mass of this black hole, this is the one I pointed out along the way, it was the best measured one. It's 6.5 solar masses. We know it extremely well. 6.5 plus or minus 2/10. And so there's its mass. And if you say 6.5 solar masses, what's the frequency of a Schwarzschild black hole at the last stable orbit? Well, I just wrote it down here. It's 340 hertz. You have to scale it from the number that I had in the earlier 220 hertz. You scale. So 340 hertz is the fastest that this Schwarzschild black hole could do. We know its mass, you see. So we know its mass. So we know what the frequency of the last stable orbit is for a Schwarzschild hole. And this thing is doing 450 hertz. So how is it doing 450 hertz, which is faster than the last stable orbit? So anyone want to say what that? It's Kerr. So this is a really good case of a rotating black hole. And so this is getting there, you know. I mean, this is the kind of thing that makes you... Now, the other thing that's very interesting is this system produces 450 and 300. So it produces an harmonic connection there. You see those two frequencies fairly often. And another system produces that kind of ratio also. Now, what you would like to do again, of course, and why would you like to do it? You'd like to get the black hole spin. And why do you want the black hole spin? Because you've already got its mass. So if you had it spin, that's it. That's, you know, the no-hair theorem. I mean, you've got it all. So you really want it spin. And I was already hinting maybe with the spectroscopy we might be able to do it on the iron line if we understood things well enough. And these QPOs, another possible avenue for getting the spin. And here we have a system that, gee, we're pretty sure it has to be spinning because the frequency is just too high for Schwarzschild hole. So in this case, it's got 300 and 450 hertz, so it has this 2 to 3 harmonic ratio that I mentioned before. And here's another one that has a 2 to 3 harmonic ratio. Another system that I mentioned at another time, actually. And now there are something like 3 models that people have developed to say, can we take these high-frequency QPOs and deduce the spin? And I don't want to go through those 3 models. That would just take a little too long. But one simple model, for example, and each one of them has their problems, but one simple model is to say that, and maybe you know this, I don't know, but if you take, like, in the Kepler problem, like in the solar system, and you take a planet or and you have it going around at the Kepler frequency, just the orbital period of the system, and then you perturb it radially, for example, so that it isn't going around a perfect circle, but it wants to go. It has also got an oscillation in the radial direction, or an oscillation out of the plane, out of the ecliptic plane, make it oscillate, and like you go push on a planet really hard and get it to do that, or set up another problem if you can't do that one, and then those frequencies in the radial direction and the z direction are degenerate with the Kepler frequency, and that's a property of that simple classical problem. But in general relativity, those frequencies are not degenerate, and so one could say, well, maybe there's some resonances going on between these different frequencies, and that's what's driving these high-frequency QPOs. And these people have pushed that particular model. And I don't want to get into the details of it, but the idea would be that, here's be the radial frequency, the z-dependent frequency, the Kepler frequency, and all of these things depend on the mass of the black hole and on the spin. And so, if you could make good enough measurements, you might be able to determine the spin of the black hole. And what's so nice is we actually measure the mass dynamically, and this is the way we really understand it. So we're not forced to try to fit 2 parameters here when we don't really understand 1. We can go only for the second one because we've already got the first one, and we have the capacity to even measure those much better. But all of the 3 models depend on strong field general relativity for producing these high-frequency QPOs, and needs to be sorted out. And here's my attitude. My attitude is that only in the last, you can see, 2001, 2002, we've got these resonances here, or whatever you want to call them, these harmonic relationships. And we've got Rossi X-ray Timing Explorer, which has an area of about a square meter of detector area. And what we need now is 10 square meters of detector area, and not 50 kilobits per second of telemetry, but we need a megabit per second of telemetry. In other words, we need a bigger mission. We're just hanging on by our fingernails to measure these things, but these things would become like ripe fruit if you had the right system, big enough telescope to really collect them. So one thing you can do that was kind of interesting, and I just did this as a slight quantitative. This is sort of a continuation of what I was just showing you. Again, here's these two systems, 1655 and 1550, and here's their frequencies, the ratios of their frequencies. And that ratio comes out to be that number. And this is Ron Remillard, who works at CSR, if any of you happen to know him. If you take the ratios of the masses that have been measured for these black holes, you get the same number. It has a rather large uncertainty, unfortunately, because of this one black hole, which is not so well measured. But it's actually the reciprocal. The point is the frequency, we expect the frequency to scale as 1 over the mass. The more massive a black hole is, the larger it is, the longer it takes to make an orbit, the lower the dynamical time, lower the frequency, rather. So you get some agreement here on this, that these two black holes are scaling approximately correctly. But again, we need a lot more and a lot better data. When you consider that all of this just came from RxTE, which was launched in January of '96, it's very impressive. I think there's with a lot of other missions coming along, I think we've got a lot of things to look forward to. And now I wanted to mention this microquasar idea, which is really just saying that these objects look like quasars. So this is the ordinary star over here, and this is the accretion disk around here, and this is a sketch that Felix Mirabel drew. And the black hole's down here in the center. And then you see these jets coming out. Well, there's been a lot of radio jets observed now. Perhaps 10 systems have had radio jets coming out, relativistic radio jets. And as opposed to the AGN type, the ones that are from external galaxies, which are kind of like frozen on the sky, these things move across the sky, and I'll show you in the next picture here. They're typically a few light years long, as indicated here. And one imagines that probably they're driven when maybe the mass accretion rate onto the black hole is just a little too high, and the matter coming in and the black hole, and people think, well, the black hole's probably spinning for these systems. And there's some evidence in a couple of cases that they are, like this one that I just showed you, the 1655 from the QPO data. And the material's coming in, and excess material just gets squirted out the axis, the spin axis of the black hole. And that's sort of a hand-waving picture of how it might go to produce these jets. But these jets exist. You can wave your hands or not wave your hands. It doesn't matter. They exist, whether, no matter what. And that's, and very recently, I should mention while this is here, the discovery of X-ray jets from these black holes. And the one system has an X-ray jet here and one on the other side, and the jets are decelerating, and they're quite a way out, and these X-ray jets are not understood. This is about a year, perhaps, no, not that old, 6 months old, something like that. So X-ray jets are yet another thing coming from these systems. But the radio jets, as I say, have been seen in 10 systems or so. And just to give you a feeling for the radio jets in, this is the large system that had 35-day period. It was at the top of the original figure I showed. GRS 1915 was 105. And this jet is coming out, the velocity of the jet, the beta is 0.92, as you see here. And this is what the jet looked like at end of March, and this is what it looked like at the end of April. So what you're seeing is there's a core source here. I guess it's marked by the X. It's stationary, right, which is really where the binary is. And then you're seeing these radio blobs coming out, and you can see that they're separating. And unlike the ones in the extragalactic case, in just a month, the two blobs are an arc-second apart. So that's a rather high proper motion when you consider this system's at 11 kiloparsecs. So, this is perhaps the best performer of the black hole jet systems, 1915. And so the jets, I would say, aren't giving you fundamental information. Maybe they will sometime, but they aren't going to. We don't know how to use them, say, to measure the spin. That's more like the spectroscopy and the iron line and the QPOs. But this is not. But this is obviously very interesting for understanding extragalactic jets and being able to study jets in a much more dynamic way. Now, in the quiescent state, when these systems are quiescent, now this is just a matter of fact, and then we can talk about the interpretation. But in this quiet state, you can measure the emission from these black holes. But as I told you at the beginning in that one diagram, instead of being 10 to the 38 or 10 to the 39 ergs per second, you're now down at 10 to the 30th ergs per second. So you can only measure them effectively with these brand new, beautiful X-ray telescopes like Chandra and XMM, if you're familiar with them. And so you have to go to very sensitive focusing optics to make these measurements. And when you do it, you find that these black holes are extremely faint, just a matter of fact. You know. And here's their luminosity scaled to the Eddington luminosity. And we have reasons for that, but it's the luminosity scaled to the Eddington luminosity. So for the black holes, that number tends to be very, very low. Now, these over here are not really, we don't have any neutron stars to compare them to, and these are not really too comparable. This is a long story, but basically these are the long orbital period systems, and in these systems the mass accretion rate is much higher, and it's just, they're not comparable to the short period ones. But if you restrict yourself to the area that's not cross-hatched here, and you compare the luminosities of the black holes, well, first of all, they're radiating at 10 to the minus 8 of Eddington. And by that I mean Eddington would be, well, Eddington is 1.3 times 10 to the 38 ergs per second for a solar mass. For a 10 solar mass black hole, it would be like 10 to the 39 ergs per second. And that's the maximum luminosity that you can get in a spherical radiator, because at that point, the scattering opacity is, the scattering, the photons coming out stop the matter coming in. The gravity is just canceled by the photon pressure going out, if you like, in the matter. So the Eddington luminosity for a 10 solar mass object is 10 to the 39, and these things are radiating at right 10 to the 31 or so. These are upper limits here. They're less than that. So the black holes are down here, and these are systems that are essentially identical, but they have neutron stars. They have neutron stars instead of black holes. And how do we know that? Because they produce these bursts that come from the surface of the neutron star, or they produce regular pulsations. They produce things that black holes can't produce. For example, a burst, a type 1 burst, is where material accretes onto the surface of a neutron star till it gets about a meter thick or so, and then the bottom of that layer gets so hot that the thing suddenly flashes and burns. And then the whole star, in a few seconds, lights up and gets very, very luminous. And such bursts don't happen on any of the black hole sources we're talking about, but they do happen on a lot of the neutron star sources. So we know these objects are neutron stars, the one that are open circles here, and they're about 100 times more luminous. So why are the neutrons, and I should say, the orbital period is the same. There's every reason to believe that the systems are the same, and the mass accretion rates are correct, and so forth. So I mean, they're really a good comparison sample to the black holes, and they're 100 times more luminous. So this depends on a mode of accretion that I haven't mentioned. I mean, I haven't really discussed in detail the accretion onto the black hole. I mean, I don't know how much of this you've covered, but in the case of the accretion disk, one has the material coming in, spiraling in, and there's friction between the gas atoms. That's the agency that produces releases the gravitational energy, because you're getting essentially GM over R. You're just getting the gravitational energy as material goes in to that last stable orbit, and it's heating the material by the friction between the gas atoms. And so you're getting this hot disk, and as soon as the heat is generated somewhere in the disk, it radiates immediately, locally. It just radiates from. That's how a disk works. It's a very efficient radiator, and it radiates very nice. However, when you get to very low accretion rates, like in this quiescent state, like these systems are in, you can show, I can't do it right now, but you can show that you cannot have this disk go all the way into the last stable orbit. It gets stopped quite a way out at 1,000 to 10,000 Schwarzschild radii. It gets stopped out there, and then you say, well, there's still material going in because we see an X-ray source, so how's it getting in there? And then there's a whole new flow pattern called the advection-dominated accretion flow model, which just means that the material is going in and it's advecting in. So by advection, you mean that the material is flowing but not radiating efficiently. So it's flowing into the center toward the black hole, but it's not radiating. But it's heating up all the time because there's still friction between the gas atoms. So the material gets very hot. And if, in an idealized case, that there would be no radiation at all, and the electrons, the ions get all the energy, more or less, because they're more massive, and they can't get their energy out to the electrons in the time that they have before they go down the hole. So what happens is a tremendous amount of heat energy is generated in this gas as it's rushing toward the center. And the flow is no longer in a disk either. It's more almost quasi-spherical in this picture. And the material is racing in toward the center. The temperature could reach the virial temperature near the black hole, which would be GM over R, which would be 10 to the 12th degrees, 1 trillion degrees. We don't know that that happens, but I mean, that's certainly a possibility. In any case, that would be about the hottest material, this side of the Big Bang. And that material, anyway, the point is, the gas doesn't have time to radiate. It finds itself heading toward the black hole. It's got all this thermal energy in it, which is the 6% of mc squared, or whatever that is achieved. And it suddenly goes through the event horizon. And that's it. It goes into the mass of the black hole. It no longer can radiate out into space. So that energy is lost. Compare that to the case of if that advected energy in that hot gas is heading toward a solid neutron star. It's going to pile into the surface of that neutron star, heat the surface of the neutron star, and that neutron star is going to radiate and produce well, 100 times more luminosity, I guess. In fact, we expected the neutron stars to be brighter than they are, and so there's some uncertainties in all of these things. Because, and for those who haven't done astrophysics, astrophysics is one of those frustrating things where, if you're in the laboratory, you can go and put a wrench on it, and you can, measure and you can line things a little better, and so we basically have to take whatever we get, and we don't always get exactly what we want, and so we can reach certain conclusions, and then we keep looking, and we find something, a better system, and so forth. But it's certainly different than physics, certainly different than physics. So I think things are very bright for this field. I think there's a lot of possibilities here, and some that I haven't mentioned, where we have a chance to get at strong field gravity. Oh, I should wind up that other discussion by saying, okay, so the neutron stars are more luminous for the reason I said. The black holes are less luminous because they have this event horizon. That is evidence for the event horizon. That's the point. That is evidence for the event horizon. Because it's only the event horizon that allows you to hide that thermal energy. So it's a strong piece of evidence for the event horizon. And that's what Ramesh Narayan and Mike Garcia and I have been saying for some time. And we have our detractors. But what are the things you can hope to do about a black hole? The spin, the mass, the event horizon is its defining property. You would like to find as much as you can. You'd like to find some evidence for that event horizon and its effects, and this is one way of doing it. But I think that with ConX, which is a very big thing that'll be able to do that spectral line work that I was talking about so much better than anything else, if we can get another Rossi X-ray timing explorer that'll measure the timing of these things, that has like 10 times the area, like these 3 tables together here, or something like this, and if we can, and the optical telescopes are amazing what you can do today to measure the masses of these things, And I know that can be done so much better, and we can go to fainter limits there too. Just to give you an idea, the first mass measurement was made in 1971. That was Cygnus X1, and then there was one in 83, and there was one in 86. And so there's 18 mass measurements now, and 11 of them have been made in the last, the last 10 years. Okay, so 11 of the 18 have been made in the last 10 years, and the reason for that is not that more X-ray novae are popping off, that they keep popping off at just the same, more or less, level, but that the optical telescopes are so much more powerful. The new 10-meter telescopes, not only are they bigger in collecting area than the 4 meters that we always had before, but the quality of the images are just so much better. I mean, you're talking 0.3 of an arc-second image some of the time. You never could talk better than 1 arc-second in the old days. So that makes a tremendous difference when you're studying galactic sources in crowded field. And the CCD detectors, which sort of got started at some level in 1985 or so, they've made a tremendous revolution because they've, unit efficiency, and they're really, you get a nice image. You're not measuring with one stinking photomultiplier, one little point or something. But you can then measure, you can fit the profile, and really do good photometry. So I just think this is a very exciting field for anyone who is maybe thinking of research in astronomy. I'll stop there. I know you want to ask questions.
Jeff, I think you conveyed.
Yeah, the field's really going ahead. We just get the instrumentation.
I hear that. Anyone listening with deep pockets?
Well, it's the only way to do it.
Students have any questions for Dr. McClintock? Ted.
Actually, a question. The 450 hertz signal.
Yes.
I mean, how do you know that's actually coming from the rotation of the accretion disk? I mean, you mentioned you didn't really know what the physics mechanism is.
Would you repeat the question?
Oh, yeah. The question is if the 450 hertz signal, whether that, how do we know, or why do we think that that's coming from the accretion disk? It's just that, no one really knows how to take and get, say, 3% of the photons to produce a 450 hertz signal in any other way. It seems like the timing belt is the accretion disk, and most people go with that, but it doesn't mean that other things aren't involved in addition to the accretion disk, including this kind of like a corona that I was talking about, the hot material around and so forth, interacting with the accretion disk. And there's a lot of sort of gooey details I could go into about the relations between that other component, this hot accretion, this hot corona that's around the accretion disk, and the accretion disk itself. But it's I mean, and people could be wrong, but the 3 models that are out there right now, all invoke the accretion disk doing something, either like this thing I was just mentioning here with the radial motion or so forth. Another one is oscillations in the inner disk that are kind of trapped, and they do an eigenvalue problem and so forth, but it's all strong field GR, and it's all radial oscillation, because again, it's in the disk. And then the third one is like lens-Turing precession kinds of things. So there's almost geodesic kinds of things. So people criticize that because how could you have really free motion in such a circumstance? But all of them invoke the disk. But we could be wrong. We could be wrong.
Yeah, I just add, we don't resolve any of these disks. No one has ever seen an accretion disk around a black hole because the angles they subtend in the sky are just too small. We're simply measuring the total light or X-ray output from these things and then making models. Nonetheless, there's really no way that we can conceive of the radiation coming from around these black holes, except through the accretion disk mechanism. So that really is the starting point for any theoretical model of the oscillations or any other property.
Yeah, yeah, like the iron line.
Molly.
Relative to the mass of the binary star and the black hole, do we have any idea how much mass might be in the actual accretion disk?
Let me just repeat that question. How much mass is in the accretion disk compared with the primary and secondary stars?
Right. Well, it's not very much. It'd probably be like 10 to the minus 9 solar masses or so. So it's really a minuscule amount compared to the other two components, the ordinary star and the black hole. People have had models in the past, but they've sort of been laughed away about very massive disks and systems and so forth. And in fact, that was one anti-black hole argument. For example, this was 15 years ago, but a person published a couple of articles saying that this object A0620, which is one of these early black holes that were found, that the disk around it was like 5 solar masses, and that it only had a neutron star in the center. There was a solar mass or so, and then then there's an ordinary K star over here, was half a solar mass or something. So you have a 5 solar mass disk around a say 1 solar mass neutron star. But then you ask yourself, well, is that disk stable? I mean, that's a pretty massive disk, and most people were able to say that that isn't stable, and it would be a big problem. But you have some ideas of the masses in these disks from various arguments about how much radiation is coming from them, and I'm trying to think of the best argument to get the mass of a disk. I can't think of a really great argument right now. I mean, if they got too massive, then you'd probably start to get into precession effects and things, and it would be some complicated dynamics. But 10 to the minus 8, 10 to the minus 9 solar masses, I think that's more or less what they are. And if you look right straight through the disk plane, you might see something like 100 grams per square centimeter, maybe up to 1,000 grams per square centimeter at most, or something like that. It's not going to be a lot.
So those disks have even less mass than the solar system disk compared with the sun, because remember, Jupiter contains 0.1% of the mass of the sun. Here, these disks have even a smaller fraction.
Yeah.
So whatever planets existed around these stars before they became supernovae, they're long gone.
Yeah, I think so.
I understood you to say that the disks emit X-rays because they're being illuminated by X-rays. Now I understand how the disks get hot by friction as the material goes in, but what is illuminating them, and where does that illumination source get its energy?
Right. I think I would perhaps confuse things slightly there. I mean, there's 5 states that black holes go into. They're not like thermodynamic states or states of a quantum system or something, but they really are rather distinct states of emission. And so I sort of blurred some of that together. But the disk itself is a significant radiator, but it's not a very hard radiation that comes from the disk. It's a thermal component that's more or less like a 1 keV black body. And it's really modeled usually as a succession of black bodies of increasing temperatures as you go in radially toward the last stable orbit. And so you have they call it a multi-temperature black body or something like that. But it's more or less 1 keV. But what you see in these systems, and I didn't bring spectra, but in these systems you see radiation that goes out to several hundred keV in what's called the very high state of these systems. And that cannot be coming from the accretion disk. That radiation that's way out there at very high energies must be coming from some other structure. And it's generally called a corona. But beyond that, there are like 30 models of the corona, and it's not a very satisfying picture that we have of the corona. And the corona must be involved in things like these very large low-frequency oscillations that I was showing earlier. They must be, again, because you look at the spectrum and you see there's a lot of hard radiation out at these frequencies and so forth. But it's not clear. It's not quite clear what this corona is, but it's material that, I mean, if I wanted to wave my hands, here's what I would say what it is. You've got this disk. It's going to have magnetic fields in it. The magnetic fields are going to erupt and so forth just by dynamo effects, more or less like the sun. And that material is going to erupt up, and it's going to be rather hot, just like the stuff that produces prominences and so forth in the sun. And it feeds into this material, this bigger structure around the disk, which is the corona. And people talk in that way about the corona, and they talk in other ways about the corona. But the understanding of the corona is very poor. The understanding of the disk is relatively good. And I'm sorry, but the other point on that is that this corona is this thing that's illuminating the disk and fluorescing the iron line, because the iron line is at like 6 kilovolts. And so it has to be radiation above 6 kilovolts that's hitting the disk. So it's pretty hard radiation that's coming from this corona that's illuminating this disk and producing this fluorescent iron line that we're seeing in this very broad iron line.
That iron line comes when you excite one of the inner shell electrons. Iron has 26 electrons. A lot of them are removed because the gas is quite hot. But if you strike iron with sufficiently high energy radiation, you can kick one of the inner shell, innermost electrons to a higher energy level, and then it will cascade back down, just like in a hydrogen atom, producing, in the case of iron, X-rays.
Right. And this was the iron K line, so this is the inner shell, the 2 electrons in the inner shell.
Right.
Yeah.
And the disk just isn't hot enough to heat the iron and excite its inner shell by itself.
Right.
If the disk were that hot, we would see blackbody radiation coming at 6 or 10 keV, and we don't.
Right. The blackbody radiation is more like 1 keV temperature, which is not enough to excite its own iron line. So, but then that was the question: how well do you understand this illuminating source that's fluorescing the iron? And the answer is you don't understand it very well, which is really unsatisfying for.
Well, we don't understand everything about these systems, but on the other hand, it's a great opportunity for learning.
Oh, yeah.
And let me just put in a plug here for any of the students and those who might be watching. A lot of the research in this field, the observational research, is being done at MIT and also at Harvard, using especially this Rossi X-ray Timing Explorer satellite. Ron Remelard's group in the Center for Space Research, together with Jeff and others, are leaders in this. And there are Europe positions available, senior theses, and so on. So if you'd like to measure the spin and mass of a black hole, here's a great opportunity. Let's thank Jeff again for a great talk.
That's really impressive.